So yes, thank you, Roberto. Thank you also to all the other organizers who might be watching this for having me here. It was a very inspiring 2 weeks, and when I accepted the invitation, I was thinking, oh yeah, this is going to be like active matter and bio stuff and so on. Then I came here for the first week. It's all about rheology. So I was like, yeah, that is right. There was even a talk on scattering by Luca. So let me just very quickly tell you what I want today. I want to show you one approach that we're using in trying to understand very viscous liquids. I mean, this comes from a theory of the glass transition, but the word glass transition is a bit loaded. You heard also about NIL. So let's I will just show you some theoretical framework that is hopefully useful. So here is a very random selection of things we heard of. I mean, this is not meant to be exhaustive, just the things that sprang to my mind when I said I can connect to this. So there was Luca Cipelletti on intermediate scattering functions. So you all remember this. You remember all about viscoelasticity from Simon Rogers and from Alessandra Bonfanti, I hope. And don't worry, I will go through these things again. We heard about amorphous materials a lot by Anaya. So that's and we I will actually maybe even show a figure on vertex models at the very end. But so let me put this on a map. Where are we? This is, I guess you can spot where we are actually geographically. That's Vienna there. Does anybody know what the gray shaded area is? Come on, this is like Viennese history. This is the one form of the Habsburg Empire. The experts will realize that even Sicily was part of it. So you can actually date the map. And the colorful shaded area is covering most of Germany and most of France. That is the ancient Franconian Empire. So the gray shaded area was about 10 to the 10 seconds ago, or let's say 10 to the 13 Brownian time steps if you use usual colloid. The Franconian Empire is a bit older, it's about 10 to the 14 seconds. So just, I mean, and people who know glasses, they easily deal with, oh yeah, we have a viscosity of 10 to the 12 Pascal seconds. So I mean, these things are really slow, just to give you this, this idea. Franconian Empire, for those who don't know, was about 800. And I was inspired to make this plot by a figure that also Anael showed from a very influential paper from the Shu group. And he explained to you the different regions that you can have in the deformation of amorphous solids and fluids. So there's somewhere here the glass transition, where down here you have the amorphous solid. Up here you have a melt. And if you are at very high temperatures and very high shear rates, you would expect things to flow more or less Newtonian. More or less boringly. And then there's this region that I want to talk about more, the so-called non-Newtonian flow regime. So just to put us on the map, with all, I mean, Anel can complain if I mean, this was just very roughly. He was starting somewhere here, and then in the second lecture also showing you about how plastic events in amorphous solids accumulate and eventually give you flow. I am coming from the yellow country, I'm in Germany, and actually that happens, it just happens to be the case that the people who do amorphous solids from the kind of perspective you heard from Anael are mostly located in France. I could remember Grenoble and Paris, maybe there are others, and the people who do this approach that I want to tell you are mostly located in Germany. There's a group of Matthias Fuchs in Constance who developed this approach with Mike Cates, who was not in Germany, but okay, never mind. We've heard a lot about the basic concepts also already. I try to be very gentle and kind of reintroduce a lot of terms that we will talk about. So I want to talk about colloidal suspensions, maybe towards the end of the talk also active colloidal suspensions. So in the theoretician's ideal, this is a colloid. And what makes it a colloid is that it's surrounded by solvent molecules that we're not going to resolve. And you all know what this does by observation. What kind of motion does it do if you just have a colloid in a thermal bath? This Brownian motion. So something that looks very random. What would you measure in order to characterize the Brownian motion? Diffusion coefficient, so basically the mean square displacement, right? So because the displacements, if it's random, if there's no preferred direction, the displacement's got to average out to 0. So it's the second moment, the mean square displacement, let's say delta r squared of t, which is really the average of the individual positions at time t. So let's write it properly. So what does a free Brownian particle do? If you tell me how, I will. Yeah, I will go a bit Brownian. So what does a Brownian particle do? It diffuses. You already said that. So in d dimensions, there's a ominous factor 2 always. There's a diffusion coefficient. It goes like time. Who remembers the intermediate scattering function? It's difficult to tell me right now, so I'm just going to write. So this is a thing that depends on the wave vector that you choose in your scattering experiment. And you can write it, I think. So this is the wave vector, and it multiplies into the displacement, and then you do an average over the ensemble. And that is, to be correct, the self-intermediate scattering function. If I write it like this, if I just say, oh, this is one particle. Actually, if there's only one particle, it doesn't matter. If I have a collection of particles, there's also the collective version of that, which says I take particle number k, and I look where this is with respect to particle number L sometime before, and then I sum over k and L over the number of particles, which I'm not, yeah, okay, I mean, these run from 1 to n. And from that, it's actually also clear you get the mean square displacement from the self-intermediate scattering function, basically by a low Q expansion, which you can easily write down. The first term vanishes by symmetry normally, and then the Q squared term gives you something related to delta R squared. There's some fiddly geometrical factors. So that also tells you that in a scattering experiment, you can get access to the mean square displacement. It is, however, difficult because you have to be at very low Q, and if the mean square displacement grows, Q has to be even smaller. So this is mostly then measured in microscopy. But just to reset the scene, I'm sorry, that was no. I wanted to flip here. Leave it out. So that's the dilute case. How do we write equations of motion for this? And I think I can also just briefly remind you, if I want to write an equation of a colloidal particle at position r times t, then the way physicists think about this is to write differential equations in time. So basically, a small change in the position should be somehow related to something that changes over time. So maybe you would write the r is proportional to dt, and if it's a Brownian system, we introduce the concept of random thermal Brownian noise. So white noise will give you a factor psi of Td here, and then the prefactor is going to be the diffusion coefficient. And again, there's a factor of 2 that is just there to annoy everyone. And there's a square root because the diffusion tells you that the square of the length grows proportionally with time. How do you update this if there are many interacting particles? Anyone? So if I have interaction forces, I will write a force here. And this will also, and this is actually a feature of overdamped Brownian motion, that you say, well, the change in the position causes, let's say a force causes a drift in the position and not an acceleration, because we are thinking of an overdamped system. And then here in front, there has to be some prefactor that fixes the units. That's the mobility mu, or the inverse friction coefficient. And these two are intimately related in equilibrium, right? So far, so good. We heard about shear flow. How can I, and this was actually in one of the talks, and sorry, I forgot exactly who it was. Let's say if I assume that the colloid now is also in a solvent that has a macroscopic flow gradient, and I assume the colloid to be small enough so that over the length scale of the colloid, it just feels a drift. So this basically is equilibrium. If the force is a potential force, I should say, I should be a bit careful here. Right? If there's an external force that pulls the particles, of course, you are out of equilibrium. And I want to add later a term that represents shear. And the way to do that is to say, I look locally, where is the particle? And I'm going to add a drift force, a drift velocity, a force I don't really distinguish up to a prefactor. So, and the local velocity in the flow field is basically given by this. It's the velocity gradient tensor times the position of the particle, where this kappa is the tensor that I can form by the outer product of the gradient and the velocity. For technical reasons, this should be transposed. This again, just to annoy everyone. But that means basically that the entries of this tensor kappa are the derivative with respect to direction beta of the velocity field in direction alpha. So if you have simple shear, this is mostly zero except for one entry, which is just gamma dot, right? So let's say simple shear. Would be something like this if you chose it to be along the xy line. So what I need later of this is this distinction that I made here. I'm going to assume that this is an equilibrium dynamic. So the system is a bunch of interacting particles that interact with the gradient force. And then I'm adding a perturbation. But the perturbation is not small. Because we're interested in this regime where there's non-Newtonian flow, where there are strong nonlinear effects because we have a high shear rate. We have a shear rate that interferes with the internal dynamics of the system. But not so high that this approach breaks down, which would be if the shear gradient would be so high that you actually feel it on the particle, then you would need to add extra terms. Now, since we're at it, how do we add activity? Who wants to have a go? Let's make this an active Brownian particle. And we heard about this too already, right? So how does the active Brownian particle go? Can we lift this a little bit, maybe? Yeah, we can. Then I can put it on that blackboard. So the active Brownian particle in my theoretician sketch looks a bit like this. It has a sense of direction, and the sense of direction is a unit vector. And then it diffuses and swims along the unit vector. So what would I do? I would say, well, notice I copy the terms from over there. I should introduce this a bit later. So this is Brownian motion. Our particles might interact. And I might also add shear flow, but I mean, do one thing at a time. And now I'm going to say, well, it swims with a velocity v0. Let's make the simplest model where the velocity is always fixed. It always swims in a given direction per unit time. And then I need to say, what does this unit direction do? And the idea of the active Brownian particle is, well, the unit direction also diffuses around. So we need to write down diffusion of a unit vector. And the rotational group is too complicated for me, so I do it in 2D, where you can basically say, oh, the director of this, I can measure all angles with respect to a chosen axis. So the director is cosine sine phi. And then I just have to write down what the angle does. And the angle will do rotational diffusion. So there will be another white noise that is specific to the angle, and it's uncorrelated with this, and then it looks like this. Right? Everyone's still there, I hope. Good. Just because it shows up in my slides and I forgot to mention it, if you want to be a bit nitpicky about the mathematics, there are actually two things. One is this term is more properly written like a random Gaussian increment, so like a Wiener increment. So you will see in my slides later on this being written as dw, where w is for the mathematician Wiener. Another thing I should point out, I can actually, I'm not going to do this, but I can actually write this in 3D, where you would write an equation for the change of the normal vector, and the idea that the normal vector should keep its length, but basically experience a random torque. A physicist would immediately write a random torque like this, probably with a minus sign and a prefactor. And that is another thing where you can go a bit crazy, that this is so-called multiplicative noise, so you need to be a bit careful if you write down these equations. So for the ones who know, this is a so-called Stratonovich differential equation and not an Ito one. Don't know about these terms on point. There's no problem. It's just something that if you model this on a computer, actually if you model this on a computer, you need to add an extra drift term to be proper, because you need to translate this into the proper Ito forward differential. Okay, so this is, you do interrupt me if I'm going too fast. This is kind of meant to be the recap and say, okay, these are kind of the concepts that have been floating around in the summer school anyway, anyhow. Yes?
I have a question about this Wiener
yes.
for computational, because I think I've already been with this problem. So it's just for derivation into scarce times, or?
This would require to go more deep into the modeling of stochastic processes. So random white noise is defined as a Gaussian with zero mean and infinitely short correlation time, right? And the Wiener is just the time integral over that. So a Wiener increment is just basically integrate the white noise over a small time step t. So if you put this together, like if you say, okay, this is by assumption Gaussian, which means it's okay to only specify the first and second cumulant and no higher ones. I don't need to worry about terms with fork size in between the angle because it's Gaussian, I know that. And if you find a Gaussian that does this, you see that the Wiener process you can basically, I'm not going to write it down, because you basically generate it from a normal distribution whose variance is 1 over dt. So the standard deviation is 1 over dt. And the Wiener process is just a random. So technically in a computer simulation, you just draw a Gaussian random number with the width of the distribution related to your time step in the simulation, and then you add that. I don't know, maybe we can discuss more that later if you have more questions. But
okay.
Now, where I want to go to is, let's say, okay, maybe we have shear flow, but let's put a bunch of other particles. So it's already here. I mean, if they interact somehow, if they don't interact, it's boring. Then I have just many free particles. If they interact, this is going to be here. So while, I mean, just this equation is easily solved. It means the displacement is already written here. Even these two terms together you can solve. That's a single particle in shear flow. You can do that. You can also solve this analytically if I draw this term. I think I will just show it on the slide. I mean, there's a famous solution for that. Maybe we do it. But there's a famous solution for the free Brownian, active Brownian particle. If I add this term, I'm lost. And that's then where things start being interesting. And maybe, yes, as a reference, let's plot the mean square displacement. We make a log-log plot because we expect power loss. We expect it to either grow linearly in time or super diffusively. And if I have a Brownian particle, it's just a boring straight line with slope 1. What does an active Brownian particle do? Who tells me? It's higher diffusion, yes. Yes. So it does something like this, and then eventually it does something like this. And here's the slope of 2, here's the slope of 1. And there's a very easy argument to see this. In the long run, all the directions are randomized, so you basically get enhanced diffusion. And if you look at the time scale where you still see the persistence in the motion, you see directed motion, which is the mean square displacement in growth. Yes. Yes. Basically, so yeah, that's a good question. So I claim there are 2 time scales. This one you can guess right easily. I guess this is if the persistence is over, and if they have a rotational diffusion coefficient. Rotational diffusion coefficient is 1/2, so this should be a time scale related to 1/dr. However, there's another time scale if I have also passive diffusion, and that's, I mean, thank you for the question. It's maybe worth pointing out there are a lot of active matter models that say I'm interested in the regime where the activity is very large anyway, so I can forget about thermal diffusion. And then I just drop this term. If I keep it, there is a time scale that basically goes like the diffusion, the translational diffusion coefficient divided by the velocity squared. That works because that is meter squared per second. This is a velocity squared, so this is a time scale. And it shows you if I switch off thermal motion, then this regime is gone and I start ballistically, which is what a lot of active matter models do. If you, I mean, I don't know, for me it was always more practical to start from a reference system that is just passive diffusive, and then we add activity to that, and I will show you the technical reason for that. So you can basically play with these timescales. And of course, that also matches if you make the activity very, very strong, this timescale also goes all the way to 0. Okay, so now maybe I go back to the presentation. So again, now I need to switch off the light. I need to diffuse over there. And so just as a summary, these are example trajectories of active Brownian particles. Berg was already cited in some of the other talks. There's a very nice and small book that he wrote, I think in the 70s, Random Walks in Biology. This is an actual trajectory of a bacterium, and he calls this the flamenco dancer for reasons that you'll see. And over there you can see the thing that I just drew with the proper factors inserted. So here I express the rotational diffusion coefficient in terms of a persistence length, and Peckley number is proportional to the velocity squared. Doesn't matter. Now, this is what happens if you put many, many particles together. Again, this is something we've been alluding to in a lot of talks at the summer school. I don't think anyone has ever showed these movies. This is actual confocal microscopy data taken 15 years ago now in the Edinburgh group. And this is the same system, and it's just a slight increase of density from left to right. And what you're supposed to see is that if you look at this, you're supposed to see nothing, right? Basically, these are just 2 snapshots of dense systems, which means the statics doesn't really change very much from one to the other. But the dynamics does. If I play the video again, you will see that in the regime that I call fluid, particles move quite a bit. And many of you have seen examples like this in very different systems. So just to convince you, it's a very generic phenomenon. And this is where the vertex models also come in. We've seen at least a snapshot, or maybe even the movie in the talk on the vertex models. This is from the same paper. And you see the transition in rigidity. So there is, at least on this phenomenological level, these things start looking very simply. This is my theoretician sketch. And basically, what is my distinction between fluid and not fluid? And for not fluid, I'm just going to call it a glass. it's if I pick any particle out of the system and I observe how far it goes. If I give it sufficient time and it moves all the way across the sample, like on the left hand, that's a fluid. If it's localized, it's a glass. And that is at least one way to try to distinguish fluids from glasses. And then the rheologist would come along and say, no, the actual way to distinguish a fluid from a solid is by doing a rheological test. Right? If I deform it a little bit and it reacts elastically, it's going to be a solid. If it starts flowing, it's a fluid. That is my distinction. So that already is this interesting thing. How do we connect the microscopic and the macroscopic pictures there? So this is what the rheologist would say. You measure the viscosity. The viscosity is finite, it's obviously liquid. If the viscosity is infinite, it's a glass. And then you can have a 100-year-long scientific debate of where is the glass transition, because the problem is you cannot really measure the viscosity to arbitrary high values. And then people even try, again, to give you an idea, I mean, glass transition people, like I was brought up with, they talk about viscosities that are 10, 14 orders of magnitude slower than the intrinsic dynamics of your system. Already something quite moderate, like only 8 orders of magnitude, gives you experiments like this, where if you want to observe droplets falling in a viscous fluid, you get, I don't know, a droplet every 8 to 12 years and so. This is in the Guinness Book of World Records for the longest running experiment in science. And if you want to model this macroscopically, again, you have this dichotomy, you have fluid-like people, everyone starts from Newton, the Newtonian fluid, and then you add things, you make things non-Newtonian, etc. Or you start from the solid, where you start as a reference model from the Hookean solid, and then you add things to it to escape from linear elasticity. And I find it funny that this is still the dichotomy that also between the different descriptions of glasses, like what Anel taught you about, coming from the solid side, saying, I need to understand spatial correlations in plastic events in the solid. What I will be telling you, I come from the fluid side, I will tell you, you need to understand temporal correlations in the fluid motion. And these things obviously need to meet at the glass transition. And there are some very interesting recent works, actually, to show how this can be reconciled, but I think it's still an interesting topic to discuss. What I find funny there is that actually, I don't know whether you know, but Newton and Hooke really hated each other. So I hope, Anna, we can still go for lunch without fighting, but these guys, they were... this is also the reason, just a side note, why there is no known contemporary picture of Hooke. This is a modern imagination of how he had looked like, because Newton was the successor of Hooke at the Royal Society in London, and he made sure to destroy every painting of Hooke because he wanted this guy to be eradicated from science history. And they fought over their theory of gravity. Both claiming to have invented it first. So they were, I imagine them like this. Anyway, so far the story, we have glasses, we have like those different things. I'm going to look at the approach to the glass as a liquid that becomes more and more viscous. But however, of course, it's a bit more complicated still. Because if the system becomes more and more viscous, it means it's more and more sluggish to react. So its intrinsic dynamic, it's slower and slower, and that means it's much more prone to perturbations on any scale. And the effect, again, this is something that Simon Rogers told you a lot about, but I just wanted to give you, it's a week ago, right? So we can repeat it. So you get nonlinear rheology effects. The viscosity is not really a constant. If you plot the viscosity, you find out it depends on the shear rate. And again, the two very different regimes. One is a metallic glass measured very close to its calorimetric glass transition temperature. So here the viscosities are really 10 to the 12 Pascal seconds. You see in the example over there, that's a colloidal dispersion. The viscosities are very low, completely different scales. But by and large, the same phenomena. And of course, we've understood by now that you shouldn't plot the viscosity as a function of shear rate. You should plot the stress, which is what you actually also measure in your rheometer as a function of shear rate. And then you get these so-called flow curves. And I think some of you at least had fun measuring flow curves or also understanding how much effort it is to measure a data point at extremely low shear rates. You have to wait forever. But it's a very important figure for me because it defines what is called the dynamical yield stress. So there's this extrapolation where you say, for all practical purposes, my flow curve never goes to 0. As it should, right? I mean, in a liquid that is not sheared at all, you would expect also no stresses. So you would expect the point at shear rate to 0, which is infinitely far over there in the log plot, you would expect the stress to be infinitely far down in the log plot. And it turns out it isn't, or there's also a long debate because maybe it eventually does decay, but there's a region where these systems really look like they have what is called a dynamical yield stress. And that's something that I will try to convince you how we try to describe it. Now, models, we've heard again last week about Maxwell models. The simplest idea of the Maxwell model is to say I have viscous element, I have an elastic element. I put them together. Alessandra was explaining this in great detail. So this is just one of the simplest model, the Maxwell model that you can do. And I just want to transform it in a form that I will be using. And that's also what she did already. At least for simple shear, you can say the phenomenological Maxwell model can be written either in differential form, which is the equation up there, or it can be written in integral form, which is just a formal solution of the differential equation. And it shows you something. It shows you that the stress response is the past shear rate perturbation multiplied with a response function, which is called g of t and t prime, and which, according to Maxwell, is just an exponential with the Maxwell relaxation time. And actually, it always amuses me. If you look into the continuum mechanics literature, probably because the Navier-Stokes equations are differential equations, all the material laws that rheologists like to throw around are very often differential equations. Just, I think, because it fits nicer the framework of solving numerically differential equations. However, for a physicist, I think this way of looking at the Maxwell model should be much more natural, because that's, if you learn statistical physics at school, you learn about Green-Kubo relations, you learn about linear response theory, you learn that a system has a response function that tells you how much of a past perturbation is it still going to feel at the present time. And this is what the dynamical shear modulus in this integral tells you. So for us, an integral equation should be much more natural. However, and this is also something I want to stress, this is linear response. Why? Because the shear rate is exactly here once and it's linear. How do I get all this nonlinear rheology? And the answer is with the Maxwell model, I don't get it. I have to upgrade the Maxwell model to something where, for example, the shear rate depends, the relaxation rate is modified by the shear rate. It turns out one rather very simplistic, but actually quite useful approach is to do something like this, to say, okay, let's assume that the system has two paths of relaxation. One is intrinsic by thermal fluctuations. This is going to take forever because the particles are blocking themselves, everything's highly viscous. But I'm also driving the system, and driving by a shear rate, I mean, then that is a rate, obviously, it's 1 per second. And this is just a normalization factor I don't want to even talk about. And I have to take the absolute value because the shear rate can be this or this, it shouldn't matter. So this is a very simple idea of saying I have two relaxation channels, and the fastest one wins. If I shear slowly, I have to wait for thermal fluctuations to make the system flow. If I shear quickly, I don't have to wait for that. And that actually describes shear thinning, because it says that when I shear more strongly, everything becomes more fluidized, right? So this is just a phenomenological model, but what I want you to take from there is that the formula up there, all the Maxwell models, and you can add elements in series and parallel and whatever, this is linear response as long as you say that your springs and dashpots and whatever are just connected to material coefficients. In order to get the nonlinear rheology, the flow curves, effects of shear thinning or shear thickening, if you see, you need to have a mechanism where this function that is under the integral depends on the shear rate itself again. And then it becomes a truly nonlinear phenomenon. And that's, I mean, then it's also horrible to deal with, but there we are. Okay? Now, even that, I claim, is too simple-minded, because here you say, okay, that's the shear rate, but what happens if my shear is not steady? What happens if I do Laos or like shear ramps or whatever? At which time are you going to put the shear rate here? And the answer is that's not known, because it's just a phenomenological model. Yes?
So in the linear case, you can either solve for sigma or do the Laos test. So you can basically interconvert between the stress relaxation modulus, the prime, the second prime, the compliance. And you can do that without problems, because you can rephrase this in many ways. Now, when you write 1 over tau n is this, and you plug it in this model, you can plug it here, or you can plug it in the...
It's not so easy. I mean, you could actually make a model where you say, I add a nonlinearity in terms of the stress. I could make the relaxation function depend on the stress and not the strain. Since this is all phenomenological, you don't know what to do. The problem comes if you look at the red curve, which is a flow curve that has a yield stress. It's not one-to-one invertible for all combinations of stress and shear rate. So then, yes, and so in all the things I'm going to tell you, for us it's always more convenient to drive the shear rate, but we will see. Still, this is still too simple, I claim, because we know from viscoelastic fluids they have strong memory effects. Like if I shear a system first this way and then I revert the shear and shear the other way, this part of the response is going to look different from that part of the response. So here's an example from experiment. This was done by Miriam Siebenberger, again on a dense colloidal suspension. This is a stress-strain curve. So the way you measure this is you start with your system at rest, and then you apply a shear rate, and you keep it running for a time, so you accumulate strain. And you measure something like the green curve, so it goes up, that's the linear regime, it has a stress overshoot. Anel talked a lot about how these curves have to be imagined as arising from individual microscopic events. And then eventually you reach a stationary state where the stress no longer changes with the strain, then the system is fluidized. And then if you decide, let's say at a strain of 0.4, I revert, and I just take the same shear rate but backwards. You measure the continuation of that curve, so the accumulated strain goes backwards, but the stress overshoot, for example, is gone. And you see that if you do this game reverting at different sections of the shear rate, if you revert anywhere before the stress overshoot, you get a yellow curve. You get something that looks just reversible. And there's a lot to be said about. Remember the talk by Simon, like the recoverable and the unrecoverable responses and all that. So for my constitutive model, for my modeling approach, it tells me, yeah, even just putting a shear rate somewhere is not enough. I need to really worry about the whole history of shear. So this is where this so-called nonlinear response theory gets. And then I want to continue soon on the blackboard a bit, basically coming back to these questions. I've thrown all these quantities on the board. The shear modulus at the bottom, or the intermediate scattering function somewhere in the middle there. And we don't really know, we don't have a good feeling of how they should look like or how to approach this. So this is where you should be like this and say, this is going to be tough, but I hope you bear with me. And I would ask Roberto to switch to the blackboard again. And, so how do we solve equations like this or this if there are strong interaction terms? And the first thing I need to do is that if you it turns out to be the nicer approach for theory, we need to convert from this equation, which is a stochastic differential equation, to an equation that describes the probability of finding the system in certain stages. So there is a correspondence between differential equations that can be written as follows. And this is now my shorthand notation for anything that looks like this. Because if you see, we have a change in the variable. Yes?
Slightly.
Yeah, okay, I will try. Sorry, yes. We have a change in one variable, and it's connected to a couple of terms that change linearly with time, and it has a couple of terms here that are random incremental in time. So I will write this bigger. The problem is that this doesn't really erase well, right? Yeah, I can. So this is how you would do it on a computer. And here you draw random increments from the Gaussian, and then you do just a simple Euler forward scheme to calculate the increment with the time step, and then you solve and you bunch of trajectories, you average over them, you calculate the probability. There's another way of looking at the same thing, which is saying I really want to describe the probability of finding a given state of the system at time t. I'm going to call that P of x and t. And the answer, I mean, the question is now, can we write a differential equation for that? Can we potentially even solve it? So the first task to do, and I don't have the time to go through the calculation in detail there. The first task to do is to say, can I map this dynamics onto an equation for this object? And the answer, I'm going to write down the answer, and then if you want, we can discuss. The answer is that yes, you can, and it looks a bit like this. So of course, these coefficients can also depend on the state of the system and time. So this is the most general form. Don't worry, I will specialize the data. So the message here is twofold. Basically, you can say, yes, instead of solving the stochastic differential equation for a billion trajectories, I can also calculate the probability distribution that tells me right away what is the probability of finding the system in such a state. And it's an ordinary differential equation. Well, no, it's a deterministic differential equation. It's a partial one, actually, so not an ordinary one, I'm sorry. It's a partial differential equation, so it has a time derivative, it has derivatives with respect to x, and x here is not just one coordinate, it's just the whole, this x you have to think of as the supervector of all the positions and orientations and what have you that describe your particle. So this is kind of the configuration space element. And that already tells you why computer simulation people rarely ever solve this. Because if you are going to simulate, let's say, 1,000 particles in 3D, not even, I mean, only spheres, then this is a 3,000 dimensional vector. So the theory of solving 3,000 dimensional partial differential equations is not really there. It's called the curse of the dimension. You basically can't do it. But still, for the theory, it's a useful approach. Yes, Sanne?
Somewhere. So
yeah.
the B is a fact because B transpose should be a scalar. Isn't it transpose B?
Okay, I'm sorry. I was not using vector and matrix notation here correctly. If I want to do it correctly, I say, okay, this is a vector. Then this is a vector because this is a scalar. Then this is a matrix times a vector because each element of the position can be driven by its own mode. And then what you have to do is you take the symmetrized square of this and contract it twice with the gradient. And then you get a scalar again. Yes, so this is a matrix, this is a matrix.
It's a double contraction with x,
it's
which
a double contraction.
Okay.
But okay, I mean, I was not trying to put too much emphasis on this, but still wanted to write things that are. So why do we care about this? Why do we think it's a useful concept in theory? Well, because we can calculate averages with it, at least formally. So let's say we have something that I call an observable. That is just a function that depends on the actual state of the system. So in this terminology, it's just a function f that depends on the variable x. It could be the average density, it could be density fluctuations to some wave number, it could be the stress tensor, anything that you can sum over all the particles and then think of as in thermodynamic. This is an observable. So what is the expected value of the observable? I mean, mathematicians now would write EF, physicists like the angular brackets. So what is the expected value of the observable? It says, well, you have to calculate your observable at all the possible states that your system has and weigh them with the probability at which these states occur. And if the probability changes over time, so will your average. And if it doesn't, then you are in a stationary state, or maybe even in an equilibrium state. And there should be a dx here. Right? So that's just also, I mean, you see this in quantum mechanics a lot. That's just a simple idea to calculate averages from the distribution functions. And so, for example, if I want to write down an equation that tells me the stress in the system is the following, I need to find the microscopic expression that gives me the stress. Many of you know already, it's basically R times F. And I need to average. So if I know this distribution function, I'm done, because then I can perform the average in principle. I could try my luck with Monte Carlo simulations, where you say, okay, I'm just going to draw a bunch of x's and hope that my integral is approached reasonably well by throwing a lot of x's in here. Then you have to worry about putting also drawing those x values where this has a lot of weight. Another story, right? And let me see where I am in my script. I'm jumping over a few things to not make it overly. So just for example, if we take Brownian dynamics, passive Brownian particle, what are these terms? And then you can, in principle, figure it out from the equation that is over there on the blackboard. I'm just going to give you the result. So the equation for Brownian particles, you can rearrange as, let me write it like this. I try to write big enough. And this is obtained by simply inserting, you see this term A, over here it was connected to mobility times the force, that's the drift term that you have. And then we had a term in front of the diffusion term, which was the square root over 2D, and the 2 vanishes magically, you take the square, you get a diffusion coefficient. And now I already assumed that the diffusion coefficient is kT divided by a friction, or kT times the mobility, so that allows me to factor this out. So that is a famous equation for colloid people. It's called the Smoluchowski equation. It is a special application of this more general formula, which is called the Fokker-Planck equation. And just to create confusion, as we always like to do, there's also another very famous equation called the Smoluchowski equation. If you ever dealt with chemical reactions and rate and diffusion aggregation, that's not I mean, it's the same Smoluchowski, but it's not the same equation. The same idea, maybe. And if you talk to mathematicians, they actually don't know the term Smoluchowski equation. For them, it's just a Fokker-Planck equation. If you talk to a physicist about a Fokker-Planck equation, it's usually something that contains the velocities still. So you see, things could be simple if we wouldn't all use different languages. So there we are, the Smoluchowski equation. And then you can think about yourself how to add the remaining terms. This term needs to go somewhere. If you want to do active particle, this term needs to go somewhere. I will show you later. Point is, for formal development, now I can make things look easy, because I can say all I have is this. Now I say this is a so-called linear differential operator. It's just collecting all the terms, because I mean, you see, I mean, I wrote it like this here: change in P equals blah, blah, blah times P. And if we forget for a bit that these are derivatives that act on this P, I can say formally, this is an operator that eats this function and produces another function. But the point now is, of course, now this looks simple. How do I solve an equation like this? Almost. So it's a time-ordered exponential. I don't know if it's really loud. Yeah, so this would be solved by an exponential. And then you can say, okay, the exponential is also defined by its Taylor expansion, so you can even do it for operators. This is a bit more tricky. But you are right, in principle, I can say if I know the state of the system at some point prior to t, and I want to propagate it to the time t, what I have to do is apply this operator exponentially. And the way this works is I have to take in the integral, You could check, because if you think, d by dt of this brings down this, and then I have to do the chain rule, d by dt just gives me the upper end of the integral, so that seems to work out. But there's an issue hidden here that I'm not going to explain for reasons of time. I'm going to say this has to be time ordered. Basically, in quantum mechanics, people would now introduce a time ordering operator and say the time ordering is that operator that sorts all. I mean, if I take the Taylor expansion here, I will get square of the integral, power of 3 of the integral, power of 4 integral, I mean, every order of integrals. And then I need to sort all the operators that appear so that they are in increasing time from right to left. And if you're interested, we can discuss this. It's a beautiful theory. I don't really need it much, but I want to be correct in what I'm writing. That's all. Now, so in principle, I'm saying that's the solution. Calculate this exponential, we're done. And of course, no one knows. I mean, otherwise, I wouldn't be talking about this, right? If people knew how to do it. Now, a special case that I want to use a bit later, the stationary solution is just defined as the solution where nothing changes over time. And if you look at this thing, it means that our operator, which is, since this is the Fokker-Planck equation, this is called the Fokker-Planck operator. So the stationary solution needs to obey that the operator acting on a solution vanishes, because otherwise I couldn't match this equation. So that tells you that this operator has an interesting property. It has a non-trivial zero subspace, or a non-trivial subspace of eigenvalues 0. Just have that. Now, well, how can we make progress with this? Remember, what I want to do is I want to calculate averages like this. And I want to replace this by something that is a bit more tractable. And let's assume that my stationary solution maybe in the infinite past, my system was in equilibrium. It was happy in equilibrium. Again, a very subtle discussion I'm not going to go into is what is the difference between an equilibrium solution and a stationary solution. There is a clear difference, but let's say, okay, equilibrium for us means d-type balance and all that. So maybe the system was happy in equilibrium an infinite time ago, and then I did things. I sheared, I added activity, and so on. Can I calculate the response to that? So an idea is to say, can we maybe write the solution at the time now minus the equilibrium solution that we hope we had a long time ago? Can we solve for that? And you will see which effect this had if we in the end then plug this in here, because it will in the end help us to replace this by an equilibrium average. And equilibrium averages we can do because Boltzmann averages we've learned. So let's see, how can I write this down? But well, I can do it formally. I can say this is, let's say I do this integral from some time t prime that I then send to minus infinity to t, and over the derivative of the function. And then I should not write t here, I should write tau, I guess. Right? So that's the fundamental law of integral calculus. The integral over the derivative is the difference between the points at the end of the integral. That didn't get us anywhere. So, however, we can plug in the formal solution of this thing. So let's say, okay, the derivative is, okay, and this needs to be an integral over tau. Let's write that here. The derivative, according to the Fokker-Planck equation, was some operator times the function. And now the function itself formally was an exponential of the operator times the initial value. And I can just plug this in, not here anymore because the board is over, but maybe I can do it there. If I know how to. Yeah, that's what this is for, right? I thought it was for grabbing attention of people. The board. it's also a much cleaner board, so you will see what we get. So let me write again. So what I did, this is just copied from over there. And then here I said, this is the solution. This was also over there. The solution is exponential operator. Now I'm writing a bit more sloppy. Yes, Anne? Yes, thank you. I should
the order exponential, yeah.
Yes. If I want to keep the generality, it's like this. I need another like this, and it should be time ordered, and so on. You see already a lot of this shrinks down. If this operator isn't actually time dependent, then a lot of simplification problems. Anyway, so the idea is the same. So you have this, and you say, okay, I'm just making things more complicated. There's no beginning. There's another step that is not entirely obvious for reasons that I never explained so far, but you would think that this is a lot of omega operators, this is a lot of omega operators, maybe I can swap them. It turns out you can't, but it turns out that by some miracle there is a relation that actually tells you, you can write this in the following. So basically, and notice there's a subtle difference. Again, I mean, if you're interested, I have lecture notes that I'm happy to distribute. I'm just trying to get the idea across here. There's a funny thing that you have to work out for half a blackboard that I'm not going to do, to show a very surprising relation that it is possible to kind of swap these operators if you also swap the times. Still no progress, right? But now I can say, let's do the following. Let's think of our idea that we do a perturbation. So if we have this operator, let's say there's an equilibrium bit of it, there's a stationary solution, and then there's a perturbation. So this is equilibrium, this is perturbation. So the way I want to apply this is to say, this is my Brownian dynamics, and then maybe here I add shear, or I even add activity, or both, or what comes to mind. And I'm splitting this equilibrium because I know the stationary solution equilibrium, it's the Boltzmann wave. So I know that e to the minus beta u, the famous Boltzmann weight, is a solution to the equilibrium problem. And I'm assuming that the potential is something that is well characterized, and that how to do integrals of Boltzmann weights I can program, so that gets me further. Now, that means that this thing here if we apply this idea of saying in the infinite past we started from the equilibrium distribution, then the first part is eaten and I just get the perturbation acting on the equilibrium distribution here. And yes?
There's a physical reason to think that there was...
There's a physical reason for?
To think that there was an equilibrium?
Yes. As I said, the equilibrium is a distribution function that only depends on your potential. And for example, if you apply a shear perturbation, it is easy to calculate how your shear forces interact with the potential, and they basically give you things like R times F or so. So this term I usually know. Also, if I do Hamiltonian dynamics and I add a perturbing term, I usually add the perturbing field times the corresponding variable. So again, the perturbation times my equilibrium distribution I can usually calculate fairly well. everything else is a mess. So that helps. And
but when your system is active, you can't do anything as much except if you turn off activity at some point, right? But if the system is always active, you can use.
But the salient assumption here is that this is why I'm insisting on I'm going to send formally time to minus infinity. The assumption is that even if I prepare my system and imagine having bacteria that I suddenly give food, or I have something light-driven Janus particles where I suddenly switch on the light, I wait for as long as it's needed. They reach the stationary state. That's an assumption, but I hope they will. And then I can work with that. The formalism I'm going through with you is called integration through transients. And you see the reason maybe, because it means that we are going to write down everything as an integral that goes from equilibrium all the way through the transient dynamics until I reach the point that I want to say something about. And we're all almost there, so thank you for bearing with me. I just want to collect the final formula. Because now what we have is the distribution function at the time that interests us. I'm going to bring this other term over and say, okay, for t prime minus to infinity, we were in equilibrium. And then this integral is just my perturbation from equilibrium. And it's formally going from all the way through to transients ever since I switched on stuff. And okay, now I just need to copy this. And I'm lazy, so just to show you that this doesn't matter, it's just the same, it's just this. And this term I said I can calculate that's the perturbation at a previous time. So we are integrating the perturbations coming from all the previous times, acting on what was our equilibrium distribution. And now let me play one of these dirty little games. I assume that the equilibrium distribution is not exactly 0 anywhere, so I multiply with it and divide by it. This is just a 1. Yeah? This didn't change anything, but it allows me to write this as a response variable in its own right. Now, can we do something with that? And my claim is yes, we can, because we can use that to calculate the average. Where was the average? The average was over there. The average of any observable, let's say the stress. You take the virial expression for the stress, the sum over all the particles, x times f. You plug it in here. You take this formula, say, okay, I get what is written over there. So what I will have is, I will just take this equation and multiply integral dx f of x with everything. So I will be able to write any average in non-equilibrium as the equilibrium average plus a perturbation. And yes, so initially this looks like this. It's an integral f of x, this funny exponential. Let's call this other thing g of x and tau. This is just the effect of my perturbation on the equilibrium distribution, normalized by it. You see that also comes in handy, because if it's a Boltzmann distribution, it's exponential. So we'll give the same exponential again. This term cancels it. I'll show you the example for shear flow in a minute. And then I had the equilibrium distribution. So you see actually already, if this is an integral over the equilibrium distribution, I can also just write it as an equilibrium average. I mean, this is nothing else. So now I have a formula that basically tells me, if you want to know the response of the system in full non-equilibrium, not assumption that any perturbation is small, it's the equilibrium term plus this integration through transients terms, where, quote unquote, all you have to do is evaluate one variable propagated in time times another variable. This is called a correlation function. It's a dynamic correlation function. So in terms of kind of object, what this is not unlike the intermediate scattering function Luca was talking about. It's with different variables. So therefore, we have to, in theory, still do a bit of work. But that's the idea. So you've written the response as an integral over a correlation function. And again, if you had any training in statistical physics, I guess most of you had, this is, in linear response theory, you calculate this and then you call it the Green-Kubo formula. This is the generalization of that because this is nonlinear. It contains the full perturbation still in the exponential operator here. So all the nonlinear perturbation terms are still in there. But that is basically it. So this is what is called ITT, or in words, integration through transients. And some people call it a formalism because it's not really, I mean, we didn't solve anything. We cannot calculate things. It's a formal manipulation that says, okay, now this is an object that you might want to think about in terms of approximations. Maybe you say, oh, it's a correlation function. It's got to decay in time, and whatever decays in time, it's got to be exponential. And then you arrive at essentially the maximum model, as I will show you. So the people who did not invent this, but brought it to the attention of the soft matter community were Matthias Fuchs and Mike Cates at the time in Edinburgh. So if you want to read, they have a bunch of papers on that. So let's take an example. Yes?
Just one question, I mean, is there, I mean, if I would forget about transient and try to do some Onsager kind of thing, where I say that my omega is some kind of force and I have a flux which is probably speed or something, can I go back to something similar? You know, if I forget about the transient and write the final thing through sort of Onsager force and flux, do I get back to something like this?
Well, the way I see I mean, yes. And to be honest, I never understood Onsager if applied to non-equilibrium, because there are some subtle assumptions behind of kind of quasi-stationarity, that you assume your process to be always almost stationary, and then you can write all the Onsager formulas, etc. I never knew whether this is true, because for me, if I deal with a system that has a very long relaxation time, and I perturb it, I'm likely to perturb it at a rate that is faster than it needs to be stationary again. So, but I don't know. There are people who use generalized Onsager formulas, and yeah, they get similar equations. Yes.
So, getting back to that very slow thing, do you have to worry about what's happening for t going to infinity, the upper limit of the integral?
In principle, I do. I mean, it's not guaranteed that this integral does anything useful if t goes to infinity. It all depends on the properties of this operator that is hidden here. So, of course, I can invent a perturbation that just makes the system explode, and then I would also expect that my observables don't ever reach a nice state. But usually you will have an operator here that has at least an eigenvalue spectrum that tells you that you have some approach to stationary state.
Then the follow-up question, can you do something like Keldysh technique, right? Where they go backwards, right?
Yes, you could. You could. In stochastic processes, I always found it more straightforward to go forward. But there's an interesting connection between those two things, yes. Okay. I will finish on the blackboard soon to give you this calculation, and then I just want to show you some stuff. So the hardest part is over. Shear flow. How do we do shear flow? And I have to remind myself how I want to do that. So we said shear flow corresponds to a perturbation, and it was somewhere hidden here. Shear flow was this. It had a term velocity gradient times position. And remember, this is a term that is a drift term, so it goes with the dt. So if I want to put it in my Fokker-Planck equation, I have to put it here. So I will get another gradient there. So shear flow corresponds to saying, okay, for each particle, I have a gradient acting on that particle times the velocity gradient tensor times the position of the particle. An highly transposed, if you wish. And of course, you can immediately ask what happens if the shear flow is not homogeneous, and I'm not going to answer that. It gets complicated. But the point is, well, in equilibrium, I said P equilibrium is e to the minus beta u. And the gradient of u is minus the force. So the gradient with respect to particle number k is the force acting on particle number k. So it's actually easy to see what is this applied to this. But you have one gradient here. Where does it act? It acts here, because d by the arcade and arcade gives you something. And it acts here. So it should give you, and basically it should give you n times the trace of kappa. Why is that? Because this acting here gives you a delta contribution, and then you sum over this in the double scalar product, so this gives you the trace of the velocity gradient tensor. And I'm not going to worry about this term too much. And then there's a term where we get, okay, we have a gradient acting on the potential that gives me another minus sign. This gives me another minus sign, which boils down to saying I'm going to write a minus here, and I'm happy if you tell me I'm wrong, because there are too many minuses to balance in my head. But there should be a factor of beta coming down. There should be this thing remaining there, and this should be a double contraction with this and the force. I said I'm not going to worry about this term. This is why theoreticians love incompressible flow. Incompressible flow means the divergence of the velocity field is zero. This is just the divergence of the velocity field. I mean, again, you can keep this term. I'm not insisting on anything, but I'm going to drop it under the notion that this is incompressible. And this is known up to a few decorating factors of one of the system volume and volume maybe T, but this is essentially the microscopic shear stress operator. Anna was talking about that. So, and you see this makes sense. This is our, okay, and this, I actually also dropped the exponential, so this divides out. So this is perturbation theory. You have a perturbation that is shear flow, and the response of the system is to create a stress that is also coupled to that shear flow. Shear flow times the stress. So this would be linear response. So this term here goes here. So here we have something times shear rate times the stress. If we want to measure the stress, we will have another stress here. So this will be stress, shear rate times stress, and that starts looking like a Maxwell model. And you give me the hook. There. So we will get something like the stress, which is the average over the shear stress, the microscopic shear stresses, is the equilibrium stress. What is the equilibrium stress of a fluid? Hopefully zero, because everything can relax, everything can rearrange, so this should be zero. And then, again, Anil has to help me out, because again, here there's a minus sign lurking around somewhere, and you get like, I'm going to write a plus, but these things don't matter, right? So basically what I get is something like this. Tau to t operator times tau times s shear stress into the velocity gradient. Something like this. And the beauty is that this is now an equilibrium average. I skipped a few steps that are formal, so that this is not exactly the correct notation. You will find the correct one in lecture notes if you want them, but it gives you the idea. So if the velocity gradient tensor is just this, simple shear, then the one that the element of the stress tensor that we are normally interested in is the xy component. Of course, there are also normal stress differences if you want them. And this in this formalism would boil down to just saying I have a shear rate at the previous time times the stress autocorrelation function. And now you might say, oh, this I knew already. Why did you make me suffer? Well, I'm suffering, I'm sweating. But the thing is, here we have figured out the formal way to do perturbation theory without doing small linear perturbation. We can do, as in quantum mechanics, we would say this is perturbation to any order, because you keep actually the shear rate dependence in the propagator. And again, a very subtle but important point is that all these quantities you now need to approximate. You need to have a good idea of a theory to approximate, but these are all equilibrium averages. And that makes it easier because you never need to worry about complicated forms of non-equilibrium distribution functions. You can all do your averages with Boltzmann things in this formalism. The price you pay is you have to integrate over the whole history of the system. And again, what can we do with that? Well, you can say, oh, if this is a correlation function, it's got to decay. If it decays, it's got to be exponential. So a simple assumption would be, let's give this a name. Let's first say this is nothing but the generalized shear modulus. And I'm writing it in a way that highlights, again, two things that you normally don't see if you discuss Maxwell models. It's a correlation function, therefore it depends on two times. You measure once, you correlate at a later time. And if you remember what Luca told you, that you normally also would like to do time averages or ensemble averages, here I'm saying, no, don't do a time average because your system might not be in a stationary state. You might decide to drive the system with oscillatory or more complex flow. So correlation functions are variables that depend on two times. And key ingredient here, this also depends on the entire history of the flow up to that time. Up to that time, otherwise it wouldn't be causal, but so you can have this complicated thing. If my simple assumption is to say G is basically an exponential, then I would, okay, now my use of tau is a bit terrible, I'm sorry. To say I don't know what it is, I know it relaxes, it's got to be exponential, then I invent a time scale, you're back at the Maxwell model. Yes?
To see the connection, discuss the connection with the Kubo.
Yeah.
So Kubo would instead consider the small perturbation.
Yes.
And then he would have shows that for small perturbation you get, because essentially you factor out the gamma dot, and then you have the viscosity, which is the integral of the correlation function expressed. Whereas here you have, as you said, you have perturbation possibly at all orders.
Yes. Yes. And essentially, if you then by hand say, I'm going to ignore this, then you're back to Kubo formalism and then all the linear response theory and so on. And it's actually surprisingly difficult to give a quantitative answer to what is a small perturbation. And you might recall I think it was Van Kampen who always used to bluff at people and say there is no linear. I mean, like if you try to estimate what should be the regime of linear response, also from amorphous solids, you know, basically there is an infinitesimal amount by which you can shear before you break the linear response assumption. So it's actually a miracle that linear response models work so well in the thermodynamic averages. But I think the word thermodynamic averages is related. But yes, so we don't make any assumption on the perturbation being small. So this, in a sense, is an exact formula, and all we have done, because it's exact, and the problem was that we've just shifted the under the carpet and said, well, then come up with something good here. And this is the bit where I was planning to tell you about, but I won't have time. I will show you some slides on that, but just to make the connection. Another connection you could make is to say, oh, if it's a correlation function, maybe it decays like a power law. So what would that give you? Does it ring a bell from any of the talks from last week? That's a fractional scholastic model. Exactly. And so on. And these are all empirical models. The beauty of this approach is also that in principle, these things, we know how to calculate. I mean, this is not just saying, oh, it's some stress. It has a clear definition in terms of position and forces. So you could think of a microscopic theory to give you an idea of what it should be. And this is the part I won't tell you about, but you could do microscopic theories. And the names in the game are the so-called mode coupling theory, which I will show some results of. But you could, in principle, also do dynamical density functional theory or whatever. Whatever is a dynamical theory that is able to predict correlation functions based on microscopic variables. And then, so that's the thing, right? So this is why, what I said, this is the nonlinear response formalism. And I will use 10 minutes now to go back to the presentation. Let's see what we got. And you will see that I'm basically skipping most of my talk, but that's fine. So I hope you don't look like this anymore. But I do, I guess. But this is basically, this was the whole story. This is when I give talks that are not meant to be better. This is kind of the whole summary of what we did so far. So I'm not going to go through it again, but it's all the formulas. You see, this is the integration to transient formula. And this is it applied to the shear stress. And here everything is also correct in tensorial deformation. If you want to do extensional flow or whatever, you don't have a shear rate here. You have something that is called the finger tensor. Biologists know it because it's a frame invariant measure of the deformation that happened. Just very briefly, why do I get excited about this? The thing, if you apply this to glasses, is basically, this is the summary. This is what you can take home. A glass means, if I approach the glass, not from Anael's side, but from the German fluid side, it's a fluid that has a relaxation time that grows and grows and grows and grows. So the relaxation time of the equilibrium fluid grows to infinity. And then I think about applying, like in the flow curve, a smaller and smaller perturbation. Like not a smaller perturbation, but let's say a perturbation with a smaller and smaller rate. So I send the time scale to infinity, but the rate of the perturbation to 0. Their product is a dimensionless number, and with two factors, one goes to infinity and the other one goes to 0. What does that tell you immediately? The order matters. Because if I have two limits where two things go to infinity, or it usually matters. So what you get, and people who have heard my talk in Vienna a few months ago, so they will know this already. So what you get is a state diagram, which is a little bit like this. So down here we have the equilibrium fluid. We have a regime where it relaxes quickly enough. That's the fluid. And we have a regime where it crosses a glass transition, where for all practical purposes, its relaxation time in the quiescent state becomes infinite. Now I apply a perturbation. And formally, you could say any perturbation. This is example for shear, but you could think of active forces as a perturbation. Something subtle happens there, but basically for now, this is the idea. If I apply a perturbation that sets a rate, then I have a time scale here and an inverse rate, a time scale there, and I can play this game of sending them to 0 individually. And the idea is basically that if I, for example, consider a quench from a flowing state back to a non-flowing state, I'm going to drop the shear rate from finite to 0. And then it matters whether I do gamma dot to 0, and it suddenly matters whether tau was infinite or not. And mathematically speaking, and that's why the whole thing, I guess, is interesting, is that this is kind of a branch singularity where you say, I have the white line that I actually never, ever reach from anywhere here, at least mathematically, strictly. And this is also the reason why glasses are non-equilibrium systems, why a glass pretty much all the time depends on how you prepared it. Because the way of preparing a glass is typically coming from somewhere up there and then quenching. And you can think of clever protocols. And of course, in reality, there is no infinite relaxation time ever. But in a mathematical picture, for me, it turns out to be useful to think of it like this. Now, I have 5 more minutes, which means I'm going to skip through most of the results. I'm going to drop this. So just, you've seen this formula before. Again, that's another way of writing the shear rate in a not so nice way. And then I told you that you can try to do a microscopic theory instead of just saying, look, that's an exponential. This is the more elaborate way of doing it. It's a theory that you can read up there on. I grew up with it, so I like it. Turns out pretty much no one in the community likes it anymore, so I'm gonna skip over it, and I'm gonna skip over all these parts. I think my computer's a bit lagging behind. I just wanted to give a very brief idea. Yeah, okay. So Roberto reminded me that I even put something about space in my abstract. So before we go to active particles, I had this idea and saying, okay, we now do something completely different. Now for something completely different. And so 5, 6, 7, 8, 9, of the once a year with experiments on board. So if you have experiments coming from soft matter or biophysical, so that would benefit from microgravity, we can talk. Because we have about 5 minutes of microgravity. The idea is simply you put things on a free-falling parabola, and they are in weightlessness for a while. And then you can do that. You can produce movies like this. This was not done on a rocket, actually, but on, it's not even playing. Okay, this is not playing. I had a nice movie of a viscoelastic fluid under a strong impact after microgravity, which is a beautiful illustration of viscoelasticity. But I guess we have to skip it. So 4 more minutes to active particles. Again, this is my sketch of active particles. So we heard a lot about much more involved models, cells that communicate, that have alignment interactions, that do fancy things. The theoretical model, we start with something humble. This is used in the glass physics community now as a very interesting model system. I think Julia said in her talk, this is not useful. This is just meant to be a very nice non-equilibrium setup system to study statistical physics. So the active Brownian particle. You've seen this before. I had it on the board. This is the equations of the active Brownian particles with an unfortunate choice of colors. You have the translation from the stochastic differential equation to the Fokker-Planck equation. You do the whole formalism again. I'm going to skip that. Maybe just one thing because it's a nice take-home message, just very briefly. How do you describe active particles? And the idea is a very fundamental quantity. If you want to build a microscopic theory of how correlation functions relax, is to start with the local fluctuating density. That's also the thing that is in the intermediate scattering function. So from this, you build the intermediate scattering function by saying, I count all my particles. I count all the particles that happen to be where I look. And if I want to do orientations, I also count the way where they happen to point. So in fact, this should be also angle dependent. This is now a 2D system. This should be a normal vector in 3D and so on. And the intermediate scattering function builds on the Fourier transform of this variable. So if I take the Fourier transform, I get e to the I q r, sum over all particles. So if we forget about this term for a moment, this would be the intermediate scattering function rho of q. Then there's a time somewhere here. Because if you write this out, this is e to the minus IQR plus e to the IQR of 0. So convince yourself, this is the intermediate scattering function. Now for active particles, you need to worry about orientations as well. Orientations are fluctuations in an angle. The angle, however, goes from 0 to 2 pi, so there's a periodicity that tells you there are kind of quantum numbers of rotation. So you get something like this, which means that the correlation functions you form are actually matrices that have indices L and L prime. So this is a bit like, it's the quantum numbers of orientation, if you say, right? You do this whole integration to transients approach for the correlation functions in order to describe active particles, and I will conclude with it just because I think it's an interesting way interesting thing to keep in mind. I need to write one more equation for that. What is the intermediate scattering function of a Brownian particle, one single Brownian particle that does diffusive motion? Does anyone know? It was in Luca's presentation, I think. Just the self-intermediate scattering function, one particle diffuses this, right? It's e to the minus q squared d times t. And you get the mean square displacement by basically looking, this is basically the mean square displacement up to a prefactor. So in the low q limit, this thing is e to the minus q squared times the mean square displacement up to prefactors. What does an active Brownian particle do? And I claim the active Brownian particle, if it's alone, also relaxes exponentially. It's still e to the minus q squared times a mean square displacement. But can you switch on again? But this is how exponential relaxation looks for active Brownian particles. So these red things with these things that you see, these I claim are just exponentially relaxing functions. And I hope you protest because exponentials should be positive. I think. But the point here is these are matrix exponentials. Because you need to take into account the active Brownian particle with its orientation. And that gives you a version of the theory where you have a lot of angular momentum indices and so on. And that's but I think I will, rather than kind of deterring you from a well-deserved break, I will just stop here and say we discuss a bit if you have more questions. And I'm not going to show the rest of the talk. Thank you.